Hi everyone. This is the problem that we gave you guys in class, and I noticed that many of you were really struggling to really calculate the probabilities that are asked for in this question. So I wanted to take a few minutes to just kind of go over some of the things that you should be doing when faced with a problem like this. So what I will do is I will walk you through how I would solve part A. And from that point on, I think it becomes a little bit easier to figure out how you'd figure out the other ones as well. So I will work through one or two problems with you guys here, and then you should be able to figure things out from that point on. So the first thing you need to do is, when you're looking at a question like this, is figure out some of the key terms. So in this case here, this question tells you that this is a recessive trait. Okay, so we have a recessive trait that we're dealing with, which means that we're going to be dealing with individuals who have it who are going to be homozygous recessive. Okay, so what you are going to be looking for is trying to figure out a way of identifying those individuals. Now, in the problem itself, you had two different colors, blue and red. I've just colored in the red ones because that's the one that was the recessive one. But you could figure this out by looking, for example, at this couple here. Or actually, no, not that couple. This couple over here, where both of the individuals do not have the trait, but one of their kids does. So when you see that the couple, the parents, do not have a particular trait, but the child does, that tells you that the child is homozygous recessive for a particular trait. And so in this case here, we would label this individual as being a little a. And so that means that the individuals in red are going to be our homozygous recessive individuals. These are the people who have this particular trait, the recessive trait that you're being asked about. Now, based on this, you should be able to figure out some of the genotypes of the other individuals in this particular pedigree. So, for example, individual in generation 1-2, this individual here, is going to have to be heterozygous because that's the only way to get this individual here. Okay? The only way for this individual here to be homozygous recessive is for this parent to donate a recessive allele to this child. So there's going to be a little a donated by the dad, but dad doesn't have this particular trait, but doesn't have this particular phenotype, so he's going to have the capital A as well. So he's a heterozygote. Okay? So now that we know this, we know that one of the parents will always donate one of the recessive traits. We also know that each of their children will have a heterozygous genotype in this case. Okay, so the ones who do not have the phenotype will be heterozygous because one of these A's is going to have to be coming from this individual here, from the mom who has the phenotype. Now, from this point on, we see that there are people marrying into this family. So, for example, this individual here, so 2-8, is marrying into the family. And the problem set actually tells you, unless there is evidence to the contrary, you can assume that the individuals who have married into the family do not carry the recessive allele, which means that they do not have a small a. So this individual here, because we don't see any evidence of any of these individuals, any of their kids having the phenotype, the recessive phenotype, we can assume that this individual is capital A, capital A. Okay? Same with this individual here. We don't see any evidence of these individuals here having the phenotype, so we're going to assume that that individual 2-6 is also capital A, capital A. In this case here, this marriage, so individual 2-1 and 2-2. 2-1 has a heterozygous genotype that we know. None of their children, though, are showing the trait, so we're going to assume that individual 2-2 is going to be capital A, based on the statement that we have in the question. And that's actually a very general, commonly used rule of thumb that we tend to use in genetics. Now, in this family here, however, you can see that we have one individual, so 3-5, that actually does have the phenotype, is homozygous recessive, which means that the only way for this individual to get this genotype is if individual 2-4 is a heterozygote for this trait. So this individual here would have to be able to donate this little a here, and this individual will have to donate this little a for individual 3-5 to be homozygous recessive. So in this case here, this assumption would not work, so this is why it says unless there's evidence to the contrary. So in this case here, there is evidence that this person cannot possibly be capital A. So this person has to be a heterozygote. Okay? So that allows us to basically start assigning some genotypes to the other individuals. So for example, in this particular family, we have female, so 2-5 is homozygous recessive. So she can only donate a little a to any of her children. So individual 311, 312, and 313 all will have to be heterozygous because they don't show the phenotype, but their mother has it, and she would only be able to donate the recessive allele. So all of these individuals here absolutely have to be heterozygous. There's no other way for them to have these phenotypes with these parents. The other ones, though, we really can't be too certain about. They could either be big A, or big A, little a. Okay? So, now that we've done this, you can do the same assignments for all of the other individuals in this particular case, and so you can figure out their possible genotypes. So basically, all of these individuals here, and here, and here, would be either big A, or big A, little a. So let's go on and try to figure out the probability, or the chance, that the offspring of the mating of 3-1, so this individual here, and 3-12, this individual here, so if they got married, what would be the chances of their kids having the recessive trait? Not just carrying, but actually showing it. So they have to be double, so they would have to be homozygous recessive. Okay, so let me just flip the page and just pull up some paper for myself to work on. Okay, so it's the same pedigree. I just have filled in some of the trait information, and again, we're focusing for part A on individual 3-1 and individual 3-12. Okay, so what we want to know is what is the probability, so the P of their child being equal to little a. Okay? And so to do that, you need to know, okay, both of these people do not have the trait. The only way for them to have a child that is little a is if both individual 3-1 and 3-12 is heterozygous. Okay? So again, 3-1 and 3-12, notice my use of the word and, have to be heterozygous, and each of them has to donate a little a allele to their offspring. Okay? So first of all, most of you got about as far as figuring out the Punnett square, where you said, okay, individual, this is 3-1, let's say, can donate either a big A or a little a, and individual 3-12 can donate a big A or little a, and so the possible genotypes of their offspring, of their children, are listed here. Okay, so these are the possible genotypes of the offspring of 3-1 and 3-12. So the probability of them having a child that has this genotype is 1 in 4. Okay, so this part here is equal to 1 in 4, but that's not the total answer. Okay, because it's a little bit more complicated. This is only true if this individual has this genotype, big A, little a, and this individual has this genotype of big A, little a. But based on the pedigree that we have, these individuals could also be or big A, big A. So what we need to do is also calculate what is the probability of these individuals being big A, little a. So the probability of this individual being big A, little a has to do with this. So again, this individual we're going to assume is big A, little a, or big A, because we have no evidence otherwise to tell us that this is not true. So we're going to assume that this person is homozygous dominant. So the probability of this person being big A, little a is going to be based on the Punnett square for these two individuals. So this will be little a by mom and big A by dad. And so in this case here, for individual 3-12, they must be. Okay, so the probability of 3-12 is equal to big A, little a is equal to 1. Okay. Now for this family, however, again, we have no evidence to tell us that this person here is heterozygous, so we're going to have to assume that they are homozygous dominant. And so in this case here, if we were to look at the parents 2-1 and 2-2, mom would donate either a big A or a little a, and dad would donate either a big A or a big A. Okay, so these are the possibilities for individual 3-1. They're either big A or big A, little a. Okay? So the possibility of them being little a is 1/2. So P of 3-1 being equal to big A, little a is equal to 1/2. Okay? So now again, the total probability or the chances that this child is little a is then equal to the possibility of the child getting this genotype from their parents, and also the possibility that the probability that this individual is big A, little a, and the probability that this individual is the big A, little a, which basically means that we're going to have to be doing the product rule, because we have to, all three of these events have to happen in order for us to get this child. Okay? So that means that the probability of child of 3-1 and 3-12 is equal to, excuse my terrible writing, is equal to AA is equal to the probability of just having a child with little a, which is 1/4, and the probability that the first parent, the mother, is big A, little a, which is 1/2, and the probability that the father, 3-12, is also big A, little a, which in this case is just 1. So the total is going to be 1/8. Okay, so the next problem, problem B. So in problem B, again, we're looking at individual 3-4 and individual 3-14. 3-14. You basically would solve it the same way. It's the same basic idea. Again, the probability of producing a child with a little a is going to be 1/4, and then you need to find out what is the probability of this person being big A, little a, which is what we already calculated for this individual here, is the same probability. And then you need to find out what is the probability that this individual, 14, yeah, this individual is big A, little a, which again is the same as this. So it becomes actually a very simple calculation at that point. A more challenging one might be the one in part C. So here we have, in C we're looking at a cross between this individual here, a mating between this individual and this individual here. Okay, so the reason why this one is a little bit more challenging maybe is because you kind of have to consider something a little bit differently. Okay, so in this case here, again, the probability of having a child with a little a is still 1/4, so that still applies. Okay, and the probability that this person here, so 3-13, is big A little a is 1. But the probability of this person being big A little a is what we still need to calculate in this case, and that's going to be a little bit different because both of the parents here are heterozygous. Okay, so if we look at these two parents here, and again we're looking at individual number 6, we want to know what is the probability of them being big A little a. Okay, well, if this female's parents are both heterozygous, which is the case here, then mom would donate these potential alleles and dad would donate these alleles. If we do the Punnett square, then their children could have the following genotypes: big A, big A, big A, little a, big A, little a, and little a, little a. Now we know that this person is not little a, so we can cross this one out. What's left now is 3 different possibilities. Okay, so this individual could be either big A, or big A, little a, but what are the chances of them being big A, little a? Well, if you look at this, we have 3 possibilities, and 2 out of these 3 possibilities is big A, little a. So the probability of individual 3-6 being equal to big A, little a is equal to 2 out of 3, so 2/3. Okay. Now once you know this, the problem becomes very simple. It becomes very similar to the rest of these problems that we have looked at so far. Okay. I really hope this helps and helps you prepare for your exams. Thanks.